Lecture 5.2, Definite Integrals. This is Rattlesnake Mountain in Washington State. Rattlesnake Mountain, elevation 3,527 feet or 1,017 meters, is located in the Hanford Reach National Monument near Richland, Washington, known as Lalique, land above the water. By the Yakima Nation, it is considered sacred by several Native American tribes. Rattlesnake Mountain is said to be the highest treeless mountain in the United States. I might mention this is one of the few slides in this lecture series that I took myself. Most of the slides were taken by my wife, Vicki Kelly. It is also interesting to note that this photo was taken from within the limits of the city of Richland, my hometown. This German postage stamp honors Gottfried Wilhelm Leibniz, who lived from 1646 to 1716. Gottfried Leibniz was a German who developed calculus independently of Isaac Newton. We use the notation developed by Leibniz for calculus. When we find the area under a curve by adding rectangles, the answer is called a Riemann sum, named for Bernhard Riemann, who lived from 1826 to 1866. The width of a rectangle is called a subinterval. The entire interval is called the partition. Subintervals do not all have to be the same size. If the partition is denoted by p, then the length of the longest subinterval is called the norm of p and is denoted by this symbol. As the norm of p gets smaller, the approximation for the area gets better. We can define area as the limit as the norm of p approaches 0 of the summation from k equals 1 to n of f of c sub k times delta x sub k if p is a partition of the interval from a to b. This expression is called the definite integral of f over the closed interval a to b. What it means is we add an infinite number of infinitely narrow rectangles. If we use subintervals of equal length, then the length of a subinterval is delta x equals b minus a over n. The definite integral is then given by the limit as n goes to infinity of the summation from k equals 1 to n of f of c sub k times delta x. Once again, we're adding an infinite number of infinitely narrow rectangles. Leibniz introduced a simpler notation for the definite integral. We say the limit as n goes to infinity of the summation from k equals 1 to n of f of c sub k delta x equals the integral from a to b of f of x dx. Note that the very small change in x becomes dx, and we've used dx to represent a very small change in x previously. Let's break this notation down. First, we have the integration symbol, which is an elongated S, chosen because integration is actually summing an infinite number of infinitely small things. A is the lower limit of integration. B is the upper limit of integration. F of x is the integrand, which is just the function that we are integrating. And x is the variable of integration, which is a dummy variable. It is called a dummy variable because the answer does not depend on the variable chosen. You could replace x in these two places with another letter, and you would get the same answer. We have the notation for integration, but we still need to learn how to evaluate the integral. In section 5.1, we considered an object moving at a constant rate of 3 feet per second. Since rate times time equals distance, we had 3t equals d. If we draw a graph of the velocity, the distance that the object travels is equal to the area under the line. After 4 seconds, the object has gone 12 feet. We have 3 feet per second times 4 seconds equals 12 feet. If the velocity varies, for example, v equals 1/2 t plus 1, the distance is s equals 1/4 t squared plus t. C equals 0 since s equals 0 at t equals 0. After 4 seconds, s equals 1/4 times 16 plus 4, or s equals 8. The area under this line is 1/2 times 1 plus 3 times 4, or 8. For that, we use the formula for the area of a trapezoid. And we notice that the distance is still equal to the area under the curve. Notice that this area is a trapezoid. What if we had v equals 1/8 t squared plus 1? We could still split the area under the curve into a lot of thin trapezoids, and each trapezoid would behave like the large one in the previous example. If the trapezoids are narrow enough, we get a very good approximation. It seems reasonable that the distance will equal the area under the curve. We have v equals ds dt equals 1/8 t squared plus 1. Taking the antiderivative, we have s equals 1/24 t cubed plus t. Plugging in 4 seconds, we get s equals 1/24 times 4 to the third plus 4, or s equals 6 2/3. The area under the curve is 6 2/3. We can use antiderivatives to find the area under a curve. And that is a really big deal because we don't have formulas for the area under every possible curve. Let's look at it another way. Let a sub a of x equal the area under the curve from a to x, where a is a constant. So if we pick a point A, the shaded area is a sub a of x. Then a sub a of x plus a sub x of x plus h equals a sub a of x plus h. In other words, a sub a of x, which is the shaded area, plus the area from x to x plus h equals the area from a to x plus h. Now we subtract a sub a of x from both sides to get a sub x of x plus h equals a sub a of x plus h minus a sub a of x. The area of a rectangle drawn under the curve would be less than the actual area under the curve. So the height of this rectangle is some minimum value of f over the subinterval. The area of a rectangle drawn above the curve would be more than the actual area under the curve. And the height of the second rectangle would be the maximum value of the function over that subinterval. So we can set up an inequality. The short rectangle is less than or equal to the area under the curve, which is less than or equal to the tall rectangle. The area of the short rectangle is h times some minimum value of f, which is less than or equal to a sub a of x plus h minus a sub a of x, which is less than or equal to h times the maximum value of f over the subinterval. If we divide everything by h, we find that the minimum value of f is less than or equal to a sub a of x plus h minus a sub a of x all over h, which is less than or equal to the maximum value of f over this subinterval. And if you haven't figured it out already, this is a sandwich theorem problem. As h gets smaller, the minimum value of f and the maximum value of f get closer together. If we take the limit as h approaches 0 of a sub a of x plus h minus a sub a of x over h must equal then the value of the function f of x. But this is the definition of derivative. So we could rewrite it as d dx a sub a of x equals f of x. Take the antiderivative of both sides to find an explicit formula for area. That gives us a sub a of x equals the antiderivative of f of x plus a constant. If we plug in an initial value, a sub a of a equals the antiderivative at a plus c. But the area from a to a is just 0, so we get 0 equals the antiderivative at a plus c, or negative the antiderivative at a equals c. So the area from a to x equals the antiderivative at x minus the antiderivative at a. The area under the curve from a to x equals the antiderivative at x minus the antiderivative at a. So we've written area equals the limit as the norm of p approaches 0 of the summation from k equals 1 to n of f of c sub k times delta x sub k, which we could write as the integral from a to b of f of x dx, or the antiderivative at b minus the antiderivative at a. Example, y equals x squared. Find the area under the curve from x equals 1 to x equals 2. So we're looking for the shaded area. We write the integral from 1 to 2 of x squared dx. We take the antiderivative and we get 1/3 x cubed, where x goes from 1 to 2. Then we plug in our limits of integration and get 1/3 times 2 cubed minus 1/3 times 1, or 8/3 minus 1/3, 8/3 being the area from x equals 0 to x equals 2, and 1/3 being the area from x equals 0 to x equals 1, giving us our answer, which is 7/3, the area under the curve from x equals 1 to 2. Now, when you work a problem like this on your homework or test, I need to see all of these steps. Not the labels in the blue, but I need to see the integral expression, the evaluated integral, or the antiderivative, with the limits listed, then the expression with the limits plugged in, and finally you work to get the answer. This is assuming that it's a non-calculator problem. To do the same problem on the TI-nspire, press Menu, 4, Calculus, 3, Integral. The integration template appears. Then insert the limits, the function, and the variable of integration. Finally, press Enter, and your answer appears. You can find this same command and save a keystroke by using a keyboard shortcut. Shift+ also returns the integral template. Here is another example. Find the area between the x-axis and the curve y equals cosine x from x equals 0 to x equals 3 pi over 2. We need to split the integral into two parts. We have the integral from 0 to pi over 2 of cosine x dx minus the integral from pi over 2 to 3 pi over 2 of cosine x dx. We have to split it because we have a positive area above the x-axis and what would come out as a negative value below the x-axis. But since areas are always positive, we need to take the absolute value, which means the opposite of the negative value. Evaluating the antiderivative, we get sine x from 0 to pi over 2 minus sine x from pi over 2 to 3 pi over 2, or sine pi over 2 minus sine 0 minus the quantity sine 3 pi over 2 minus sine pi over 2, or 1 minus 0 minus the quantity -1 minus 1, or -3. On the TI-nspire, we enter the integral from 0 to 3 pi over 2 of the absolute value of cosine x dx. We can find the absolute value symbol by using the template key. And when we press enter, we get the same answer, 3. If you use the absolute value function, you don't need to find the roots.